As dawn rose over the devastated shoreline, the battle for the Pacific entered one of its most intense chapters. Near Red Beach 2, American Marines prepared to hold their fragile foothold against a determined counterattack. Among them, Corporal William Dean inspected his unit's defensive position, checking that every weapon was properly set and ammunition belts were ready. Around him, other crews worked in the haze and coral dust, their movements calm but deliberate, every man aware of what was coming. Moments later, the still morning erupted into sound. From the other side of the island, coordinated Japanese units began advancing in force. The rattle of automatic fire echoed across the ruins, a mix of distinct rhythms as both sides unleashed their weapons. It was here that the contrast between the two nations' military doctrines became unmistakably clear. The American forces relied on a new generation of air-cooled automatic weapons, compact, dependable, and capable of maintaining continuous support fire under harsh island conditions. These weapons reflected years of industrial design focused on simplicity, reliability, and ease of use. Crews could transport them quickly, set them up within seconds, and maintain a steady stream of suppressive fire that shaped the tempo of every engagement. By comparison, Japanese defensive weapons, while crafted with precision and care, struggled under the weight of older design philosophies. Many of their crew-served guns were heavy, complex, and required constant attention to maintain. Ammunition feeding systems limited how long they could fire without pause, and their tightly fitted mechanical parts were more vulnerable to the island's sand, moisture, and debris. These engineering challenges often forced Japanese gunners to focus more on keeping their weapons operational than on sustaining coordinated fire during fast-moving combat. What unfolded at Tarawa became a textbook demonstration of how industrial design and tactical doctrine could decide the outcome of close engagements. American teams, supported by standardized logistics and field training, maintained consistent fire coverage across their sectors. Their lighter, belt-fed automatic weapons allowed them to reposition quickly and react to any breakthrough attempts. In contrast, the heavier Japanese weapons, though accurate and powerful in short bursts, could not maintain that same tempo once the battle intensified. This difference wasn't merely mechanical, it represented two philosophies of war. The American emphasis on adaptable, mass-produced weapons reflected a modern understanding of warfare as a contest of endurance and coordination. The Japanese approach, shaped by earlier conflicts, still placed great faith in precision craftsmanship and individual skill traits that, while admirable, could not easily compensate for the logistical demands of prolonged combat on isolated islands. By the end of 1943, the results were evident. The U.S. military's focus on practical reliability and high-volume production ensured that nearly every Marine division could deploy hundreds of identical, easily maintained automatic weapons. This consistency simplified training, maintenance, and resupply, creating a level of battlefield efficiency few other nations could match. The Japanese, limited by both industrial output and adherence to pre-war doctrines, faced growing difficulty maintaining sustained firepower parity across the Pacific. The confrontation at Tarawa would go down not just as a costly victory, but as a pivotal moment in the evolution of modern infantry warfare, proving that the balance between design, logistics, and tactical innovation could decide the fate of entire campaigns. The precisely fitted parts, which might have impressed in peacetime demonstrations, became a liability when exposed to combat conditions. Unlike the M1919's loose tolerances that accommodated battlefield contamination, the Type 92's tight tolerances meant that even small amounts of debris could render the weapon inoperable. The feed strip system itself was problematic. The 30-round metallic strips were fragile and easily bent or damaged during transport and combat. Each strip took precious seconds to load, during which the gun could not fire. In contrast, American gunners could link multiple cloth belts together, creating continuous ammunition feeds of 500 rounds or more. The Type 92 also featured an unusual sight placement, offset to the right rather than centered, which complicated training and reduced accuracy during rapid target engagement. Japan produced approximately 45,000 Type 92 heavy machine guns throughout its entire production run, from 1,932 to 1,000 M1945. Tokyo Gas and Electric Company, along with Hinino Motors and Hitachi, manufactured these weapons with meticulous attention to PSIM standards that proved unsuitable for mass production. Each Type 92 required extensive hand-fitting of parts, making them expensive and time-consuming to produce. The United States, by contrast, manufactured nearly 390,000 M1919 machine guns during World War II alone, almost 9 times Japan's total production. This staggering disparity revealed the essential mismatch in industrial capacity between the two nations. The production philosophy differed dramatically. American manufacturers used automotive industry techniques, with General Motors' Saginaw division applying assembly line methods perfected for automobile production. Parts were completely interchangeable between manufacturers. A gun made by Buffalo Arms could use parts from Saginaw or Rock Island Arsenal without modification. Japanese Type 92 seconds often required individual fitting of replacement parts, as the handcrafted nature of production meant that components from one gun might not fit another. By 1944, American factories were producing more M1919s in a single month than Japan produced Type 92 seconds in an entire year. At Henderson Field, Guadalcanal, the night of October 24th to 25th, 1942, proved the importance of reliable automatic weapons. While Sergeant John Basilone earned his Medal of Honor manning M1917 water-cooled guns, M1919 of 4 crews throughout the marine perimeter demonstrated the air-cooled weapons advantages. When Japanese forces of the Sendai Division attacked, marine machine gunners with M1919 seconds could reposition their lighter weapons quickly, moving to threatened sectors while the heavier water-cooled guns remained in fixed positions. Private First Class Mitchell Page, who also earned the Medal of Honor that night, described the M1919's role. The air-cooled 30 seconds were our mobile reserve. When the Japs broke through, we could grab the gun and tripod and run to plug the gap. At Tarawa in November 1943, Marine machine gun crews proved the M1919's versatility in amphibious warfare. Despite being soaked with seawater during the landing, M1919s were quickly put into action. Corporal James Russell of the 2nd Marine Division destroyed multiple Japanese positions with his M1919A4, advancing the gun by hand across the coral-strewn battlefield. The gun never quit, Russell later testified. We'd dump water from our cantons on the barrel to cool it, wipe the sand off the belt, and keep firing. We burned through 10 boxes of ammo, 2,500 rounds, and never had a stoppage. The Japanese Type 92 seconds defending Betio Island, by contrast, suffered constant malfunctions from coral dust mixing with the oiling system. The Battle of Saipan in June-July 1944 provided perhaps the most dramatic demonstration of American machine gun dominance. During the massive Banzai Charge of July 7th, when 4,000 Japanese soldiers attacked American positions, M1919 crews of the 27th Infantry Division created interlocking fields of fire that turned the assault into a slaughter. Sergeant Thomas Baker's M1919 crew fired continuously for 6 hours, going through case after case of ammunition. We had spare barrels ready, his assistant gunner Carl Morrison recalled. When one got too hot, we'd swap it out in 10 seconds and keep shooting. The Japs just kept coming, and we just kept killing them. Our gun alone must have dropped 200 of them. On Peleliu, in September 1944, the M1919's reliability in extreme conditions became legendary. Marines fighting in 115-degree heat found that while Japanese Type 92 seconds seized from thermal expansion of their precisely fitted parts, M1919s continued functioning. Corporal Sterling Mace observed, "The Woodpeckers would fire a strip or two, then go silent, jammed again. Our 30 seconds just kept hammering away. We knew we had fire superiority, and that gave us the confidence to keep advancing." By early 1945, during the operations in Manila, military technology had reached a turning point. The conflict in dense urban areas revealed how essential mobility and reliability were for modern infantry units. American forces utilized the M1919 Browning, a machine system emphasizing adaptability and ease of repositioning. The weapon's design allowed a two-person team to transport, assemble, and operate it efficiently, even in confined city streets or unstable structures. The total weight of around 45 pounds offered a balance between strength and flexibility, allowing for smooth movement between vantage points. Military reports from the field emphasized that the ability to relocate quickly and maintain continuity of support was often the deciding factor in success. Crews could reposition the weapon in seconds, maintaining coordination with advancing or defensive elements. In contrast, the Japanese Type 92 represented a heavier, more static design philosophy. The complete system, exceeding 120 pounds with its mounting hardware, required greater effort to operate. Once installed, repositioning it was slow and difficult, a disadvantage in constantly shifting environments such as city ruins or dense vegetation. The M1919's lineage dated back to the First World War. Its predecessor, the M1917, relied on a water cooling system that worked well for prolonged operation, but was cumbersome. Engineers sought to reduce dependence on heavy water jackets, leading to the air-cooled concept in 1919. John Moses Browning's team focused on practical functionality. They built a weapon that was simple to maintain, mechanically durable, and capable of continuous operation with minimal adjustments. Over the next 2 decades, the U.S. Ordnance Department conducted rigorous field evaluations, refining the model through successive prototypes. By the mid-1930s, the M1919A4 had become a standard tool, reflecting lessons from years of user feedback. Every modification from the improved barrel to the simplified belt feed served one purpose: operational reliability under any condition. The gun's chambering in the 30-06 Springfield cartridge provided a balance of accuracy, manageable recoil, and sufficient range. The standardization of this ammunition simplified logistics, ensuring consistent performance across the vast American supply network. Meanwhile, Japan pursued its own path of modernization. The Type 92, based on the earlier French Hotchkiss design, embodied the nation's meticulous approach to engineering. Each unit was assembled with great attention to detail, often requiring manual fitting of components. While this craftsmanship ensured precision, it also created challenges for large-scale production and field durability. The weapon featured an internal lubrication system designed to keep cartridges feeding smoothly, but in tropical climates, the oil tended to attract dust and moisture. This led to reliability concerns during extended operations. The feeding system, which used rigid metal strips of ammunition, also limited sustained operation. Troops often needed to pause frequently to reload, which reduced overall continuity compared to the belt-fed American design. Captured military reports and post-war analyses later showed that Japanese engineers were aware of these limitations. The documents indicated an understanding that the Type 92 was well suited for fixed defensive positions, but less adaptable to the mobile, fast-paced style of modern warfare that was becoming dominant by 1944, 1945. The differences between the M1919 and Type 92 reflected deeper contrasts in national military philosophies. The United States focused on mass production, mechanical simplification, and modular repairability. American factories like General Motors' Saginaw Division and Rock Island Arsenal could produce tens of thousands of standardized units monthly, ensuring every platoon had identical, interchangeable parts. Japan, on the other hand, emphasized craftsmanship, precision machining, and traditional skill. This resulted in beautifully made but slower to produce equipment, less suited for industrial-scale replacement or field interchangeability. These contrasting doctrines mirrored broader national trends: the American preference for scalable technology and logistics-driven warfare versus Japan's reliance on individual expertise and discipline. By the end of World War II, the M1919 had evolved into one of the most influential automatic support weapons ever produced. Its adaptability made it suitable for infantry, vehicle, and aircraft use alike. The Type 92, while respected for its build quality, symbolized the limitations of over-engineering in a rapidly changing era of mechanized conflict. Metal feed strips, used in some early crew-served systems, were fragile and required frequent replacement. By the time teams stopped to change them, opposing formations had often already changed the situation on the ground. Colloquial nicknames arose in field reports to describe the distinctive sound of certain automatic systems. Such references reflected how strongly equipment characteristics influenced perceptions of operational effectiveness. Post-war inspections and captured documents later offered candid analysis. Reports recovered from a naval base review concluded that one heavy crew-served weapon family under observation proved generally less adaptable in the specific conditions encountered, while the American automatic series achieved greater continuity of support in comparable situations. Recommendations for major redesign were often impractical due to production constraints, and some units were ordered to compensate through endurance and tactical adjustments rather than technical fixes. The American production effort, by contrast, exemplified industrial standardization at scale. Factories across the country ramped output while preserving interchangeability. Parts produced in one plant fit units from another without modification. That standardization simplified repairs in the field. Components could be swapped between manufacturers, and damaged units could be cannibalized for spares with predictable results. Quality control used statistical sampling and strict specifications to keep standards consistent, even as monthly output increased dramatically. Industrial technique played a decisive role. Automotive factories repurposed assembly lines and retrained workers. Steering column machinists learned to produce small arms components, and assembly line organization, specialized tooling, and division of labor replaced bespoke handcrafting. These practices increased throughput and, in many cases, improved field reliability by simplifying mechanisms and removing unnecessary complexity. One major contractor reached monthly production figures that dwarfed the annual output of comparable foreign manufacturers. Conversely, production trends for some foreign systems showed deterioration as the conflict progressed. Early units displayed fine fit and finish, consistent with peacetime manufacturing standards. Later examples, however, evidenced compromises: rougher machining, simplified fittings, substitutions of materials, and less care in finishing. Scarcer raw materials led to alternative alloys and parts that were more prone to wear or fracture. Components that once had been steel forgings were sometimes replaced with lower-grade castings. Non-structural handles and fittings shifted to less durable materials. These changes, while understandable under resource pressure, reduced overall durability and increased the need for depot-level repair. Features intended to solve mechanical issues sometimes introduced new vulnerabilities. An internal lubrication mechanism designed to aid feeding under ideal conditions became problematic in humid or particulate-filled environments. Oil attracted contaminants and increased stoppage rates unless rigorously cleaned. As manufacturing precision declined late in the conflict, such subsystems became less reliable, and captured late production examples often required thorough rebuilding before returning to service. On the ammunition side, the United States benefited from both scale and packaging innovation. Centralized ordnance facilities produced standardized cartridges in enormous quantities that functioned reliably across the national stockpile. Moisture-resistant packaging and coordinated logistics prevented many of the environmental degradation problems that afflicted other supply systems. By mid-war, aggregate ammunition output reached unprecedented levels, ensuring that units could sustain prolonged operations without the supply interruptions that had hampered forces earlier in the century. Parallel innovation improved ordnance performance and flexibility. New projectile types and specialized loadings were developed for particular roles. Improvements that emphasized consistent functioning within the standardized supply chain. Incremental design changes and factory modernization further reinforced interchangeability and ease of maintenance. Manufacturing scale also enabled iterative weapon variants, responding to operational feedback. One later model added ergonomic features and a lighter carriage option to enhance portability and multi-purpose use. Field units experimented with practical modifications, and many of those grassroots innovations informed formal changes in later production blocks. Taken together, these developments illustrate how industrial organization, production philosophy, and logistics can shape the operational profile of weapon systems as much as their original engineering. Field experience often sparks practical innovations. One well-known example is the Basilone bale, a simple wire and wood handle developed from frontline feedback and later standardized for production. Designed to allow crews to handle hot barrels safely during rapid replacement, the device exemplified how operator solutions influenced formal design updates. Marines and other units experimented with various mounts and adapters in the field. Some early attempts to fire lighter automatic systems while advancing proved impractical in sustained operations, but other improvisations were more useful. Makeshift anti-aircraft mountings fabricated from salvaged materials enabled existing systems to assume additional roles against low-altitude aerial threats. Tank crews also welded extra mounts to vehicle exteriors to broaden their coverage. The relative mechanical simplicity of the weapon systems made these field alterations feasible with basic tooling and limited technical training. Ammunition supply and standardization proved decisive. One side benefited from large-scale, highly standardized production of a single cartridge type, packaged to resist moisture and allow long-term storage and global distribution. Centralized manufacturing and coordinated logistics meant that rounds produced in different facilities were interchangeable, simplifying supply chains and depot repairs. Conversely, the other side faced difficulties producing and fielding consistent quantities of its specialized cartridge. Multiple, non-interchangeable variants of the same caliber complicated resupply and created compatibility problems in frontline units. The small, rigid feed strips used in some systems were fragile, susceptible to deformation from handling, and vulnerable to humidity factors that reduce their operational availability in austere climates. Where one logistic approach emphasized linked fabric belts and indefinite continuity, the other relied on discrete metal strips that required frequent replenishment and careful handling. Industrial organization shaped equipment reliability as much as original engineering. Large American contractors adapted mass production techniques from civilian industry, retraining automotive workers, implementing assembly line specialization, and using standardized tooling. This approach achieved both high throughput and interchangeability. Parts from separate factories fit together without modification, and statistical quality control maintained consistent standards, even as output ramped dramatically. Such scale allowed rapid field repairs and straightforward spare parts management. Over time, manufacturing conditions under resource strain led to visible changes in build quality for some foreign productions. Early peacetime examples showed meticulous finishing and tight tolerances. Later, wartime examples reflected compromises, coarser machining marks, simplified fittings, and substitute materials. These substitutions, driven by scarcity, sometimes increased failure rates and raised the need for deeper depot-level maintenance. Certain design features intended to solve mechanical problems introduced new vulnerabilities in harsh operating environments. An integrated lubrication subsystem that improved feeding under controlled conditions could attract particulate matter in humid or dusty climates, increasing stoppage rates unless rigorously cleaned. Likewise, precision-fitted parts provided excellent accuracy under ideal maintenance regimens, but were less forgiving when field cleaning and spare parts support were limited. By contrast, simplified mechanisms with looser tolerances often proved more tolerant of contamination and easier to maintain at the unit level. These trade-offs, precision versus ruggedness, craftsmanship versus interchangeability, manifested repeatedly in frontline performance across diverse theaters. Doctrinal differences shaped how systems were used. One force emphasized straightforward, repeatable procedures for rapid barrel changes, belt handling, and immediate action drills. Crews practiced teamwork operator, assistant, ammunition handlers, until tasks became instinctive. Practical skills, quick component swaps, auditory recognition of malfunctions, and coordinated displacement between positions were drilled repeatedly, enabling small teams to sustain operational tempo with minimal supervision. The other force trained crews to achieve high individual system accuracy and conserve limited ammunition through deliberate, short bursts. That approach reflected both logistical realities and institutional emphasis on precision. While a Japanese Type 92 crew carefully aimed at individual Marines, 3 or 4 M1919s would simply obliterate their position with concentrated fire. The M1919's reliability became legendary among Pacific veterans. Stories circulated of guns that continued firing after being buried in sand, submerged in seawater, or caked with volcanic ash from Iwima. The loose tolerances that some critics cited as reducing accuracy actually allowed the weapon to function when fouled with debris, a crucial advantage in Pacific combat conditions. Marines reported M1919s that fired continuously for hours, with crews pouring water from their cantons onto the barrels to keep them cool enough to continue shooting. One famous incident on Okinawa involved an M1919 that had been blown off a cliff by a Japanese shell falling 30 feet onto rocks. The gun was recovered, the bent tripod replaced, and it continued firing for the remainder of the campaign. Another M1919 on Guam was recovered from a swamp where it had been submerged for 3 days. After basic cleaning and lubrication, it functioned perfectly. These stories, verified by after-action reports, built confidence in American gunners who knew their weapons wouldn't let them down. The M1919's simplicity contributed to its reliability. With only a few moving parts, bolt, barrel, and feed mechanism, there was little to go wrong. The recoil operation meant that as long as ammunition was feeding, the gun would cycle. Even worn-out guns with excessive headspace would continue functioning, though accuracy might suffer. Field maintenance required only basic cleaning and lubrication with any available oil, including motor oil, cooking oil, or even coconut oil. In emergencies, the Type 92's reputation was exactly opposite. American Marines learned to listen for the telltale silence when Type 92 seconds jammed, using these moments to advance or reposition. The oiling system that was supposed to ensure reliability became the weapon's greatest weakness. In the humid jungles of Guadalcanal and New Guinea, oil mixed with moisture and plant debris to create a grimy paste that seized the mechanism. On the coral at holes like Tarawa and Poliu, fine sand combined with oil to create an abrasive compound that destroyed the precisely fitted parts. Veterans reported that captured Type 92 seconds were essentially useless without extensive maintenance. Even when properly cleaned and serviced, they required constant attention to keep functioning. The feed strips would rust in the humid Pacific air, binding together and refusing to feed. The oil pump would clog with debris, requiring complete disassembly to clear. The precisely fitted parts would seize from thermal expansion in the extreme heat. American intelligence concluded that the Type 92 required 5 times the maintenance hours of an M1919 to remain operational. The Battle of Okinawa from April to June 1945 provided the final bloodiest comparison of these weapon systems. American forces had refined their machine gun tactics through 3 years of Pacific combat. M1919 crews worked in perfect coordination, creating interlocking fields of fire that made Japanese attacks suicidal. The battle's intensity meant that machine guns fired almost continuously for days at a time, providing the ultimate test of reliability and sustainability. During the massive Japanese counteroffensive of May 4, 1945, American machine guns faced human wave attacks of unprecedented intensity. M1919 crews from the 96th Infantry Division fired without pause for over 12 hours. Staff Sergeant Beaufort Anderson's machine gun section expended 30,000 rounds in a single night, wearing out 6 spare barrels, but never experiencing a stoppage. "We just kept feeding belts and changing barrels," Anderson recalled. "The gun never quit. Bodies piled up in front of our position until they blocked our field of fire, and we had to shoot through them." Japanese Type 92 crews at Okinawa fought with incredible bravery, but were hamstrung by their weapons limitations. The inability to sustain fire meant that American forces could advance between reloading cycles. The 30-round strips were expended in seconds during intense firefights, leaving crews desperately trying to reload while under return fire. When Type 92 seconds did score hits, the psychological effect was minimal compared to the overwhelming streams of fire from M1919s that could sweep an entire area clear of life in seconds. The cave warfare that characterized much of Okinawa's fighting highlighted another advantage of the M1919. The practical value of a weapon system often became clearest in the tightest environments. Because of its lighter and more modular design, American units were able to carry and deploy their support weapons deep inside cave networks and confined structures, areas where mobility and quick repositioning were critical. In similar conditions, the heavier counterpart systems, weighing more than twice as much, proved far more difficult to relocate once emplaced. Field assessments and post-operation reports consistently reflected this difference. Many heavy units from opposing forces were found fixed in position, their mobility severely limited once installed. Numerous examples discovered in captured areas were inoperable or had been deliberately disabled to prevent further use. Statistical summaries from late war campaigns illustrate the imbalance. Hundreds of heavy machine guns were recovered, but only a small percentage were still functional. In contrast, the lighter, air-cooled American systems continued to operate reliably, even after years of service under harsh conditions. Industrial capacity proved to be one of the most decisive elements in modern warfare. The United States produced nearly 390,000 M1919 machine guns across all variants, while total production of the Japanese Type 92 barely exceeded 45,000 units. This near 9-to-1 advantage translated directly into battlefield flexibility. American units could deploy multiple guns per company, maintain overlapping fields of fire, and ensure replacements were always available. Japanese units, constrained by production and supply, were forced to conserve ammunition and rely on limited reserves. Ammunition supply followed the same pattern. The United States achieved massive standardization. Every 30-0, 6 cartridge produced, whether in Denver, Street, Louis, or Salt Lake City, could function perfectly in any M1919. Ammunition was sealed in moisture-resistant containers that preserved reliability in humid climates. Meanwhile, Japanese industry faced shortages of brass, propellant, and precision machinery, producing several incompatible 7.7mm cartridge types. This lack of standardization complicated logistics and maintenance in the field. Mass production encouraged a philosophy of simplification and interchangeability. The M1919 and 19's design used relatively loose tolerances and standardized parts, allowing any replacement component to fit any gun regardless of manufacturer. This meant frontline units could rebuild damaged weapons using parts from other systems with minimal tools or expertise. Production plants applied automotive assembly line principles, division of labor, specialized tooling, and statistical quality control to ensure reliability at scale. By contrast, Japan's emphasis on precision craftsmanship produced weapons with excellent individual fit and finish, but reduced tolerance for field wear and environmental exposure. As resources dwindled and material substitutes became necessary, late war examples suffered from inconsistent metallurgy and declining reliability. The complex oiling mechanism, originally intended to improve extraction, often created more problems than it solved when exposed to tropical conditions. Combat experience led to many creative modifications. Marine and Army teams developed practical tools and mounts that improved flexibility, such as barrel handling devices for quick displacement, improvised anti-air mounts built from salvaged parts, and vehicle mounts for auxiliary defense. These adaptations demonstrated the M1919's mechanical simplicity. It could be modified, repaired, or reconfigured with basic tools and minimal technical training. Japan, however, struggled to introduce design improvements. Even small modifications like improved drainage or simplified feeding mechanisms were rarely implemented due to production constraints and the risk of disrupting existing tooling. As a result, the Type 92 that entered service early in the war remained largely unchanged by its end. American training emphasized efficiency and teamwork. Gun crews learned immediate action drills until jam clearing became automatic. They practiced firing in short, controlled bursts, relocating positions quickly, and coordinating overlapping fields of fire. The emphasis was on simplicity, speed, and adaptability qualities, reinforced by the weapon's manageable weight and intuitive operation. Japanese doctrine, by contrast, focused on precision marksmanship and ammunition conservation. The Type 92's slower reload cycle and smaller feed strips made sustained suppressive fire difficult. shaping tactics that emphasized deliberate single or short-burst engagements. Japan's approach to small arms design reflected a longer military tradition that prized individual skill and precision workmanship. The heavy, finely fitted systems exemplified that ethos, exacting manufacturing practices, close tolerances, and an emphasis on accuracy under ideal maintenance conditions. These traits were rooted in cultural and institutional preferences for craftsmanship and marksmanship, but they were not well aligned with the industrial demands of sustained, wide-area operations. By contrast, the American model prioritized industrial scalability and logistical resilience. Weapons were designed to be produced by high-volume factories, maintained by minimally trained crews, and supported by standardized spare parts and ammunition. That approach favored resilience in harsh environments and under intensive operational tempos, qualities that proved decisive across extended campaigns. The practical consequences of these differing philosophies were profound. Systems optimized for high, continuous output and rapid servicing allowed formations to operate with a degree of tactical freedom that was difficult to match with equipment requiring meticulous upkeep. Where one supply network could furnish vast quantities of standardized ammunition and replacement components, the other struggled with multiple incompatible cartridge types and brittle feed components that demanded careful handling. Faced with this disparity, some formations adopted high-risk close-contact tactics to mitigate the opponent's material advantages. In operational terms, these were attempts to reduce the effectiveness of long-range volume by closing distance rapidly. Such approaches reflected grim arithmetic as much as doctrine. When sustained output and resupply are limited, alternative methods of engagement inevitably emerge. Over time, the cumulative effects of production, logistics, and equipment design shaped operational choices at every level. Quantitatively, the imbalance was stark. Aggregate production of the American automatic series totaled in the high hundreds of thousands, while the other side's production remained an order of magnitude smaller. Ammunition, manufacturing, and protective packaging also favored the larger industrial base. Standardized cartridges and moisture-resistant storage allowed prolonged operations in humid climates without degradation. The smaller industrial system produced several non-interchangeable cartridge types and feed components that were more vulnerable to environmental damage and handling wear. When measured across thousands of individual encounters, the result was a compounding advantage. Units equipped from a large, standardized pool could deploy multiple support systems per formation, train crews on uniform procedures, and rotate equipment for maintenance without interrupting operational tempo. The smaller-scale producer could not match that redundancy. Each asset required closer attention and represented a more significant investment in scarce industrial capacity. Post-war technical assessments validated these observations. Controlled tests documented that the high-output, belt-fed systems maintained operational continuity far longer between reloads, and were more tolerant of contamination and rough handling. Mechanisms relying on precision-fitted parts and assisted feeding systems performed well under ideal servicing, but became increasingly brittle under protracted, resource-constrained conditions. Analysts concluded that robustness, interchangeability, and manufacturing scalability frequently outweigh peak laboratory performance in sustained field operations. The broader lesson extended beyond armaments. Standardized production enabled entire logistics chains, from munitions and spare parts to training materials, and maintenance doctrine to scale and remain dependable. This multiplicative effect meant that superior industrial throughput translated directly into operational flexibility. More units in the field, more spare components on hand, and more crews trained on identical procedures. Technological lineage also followed from these wartime experiences. Concepts emphasizing quick-change components, belt feeding, and modular mounts became central design features in subsequent generations of support weapons. Later systems adopted the practical refinements that had proven effective at scale: simplified maintenance routines, interchangeable parts, and production methods compatible with mass manufacturing. In sum, the contrast between the two approaches illustrated a fundamental tenet of modern conflict. The interaction of design, manufacturing, philosophy, and logistics often determines long-term effectiveness more decisively than the raw technical specifications measured in isolation. The ability to sustain fire, to turn killing into an industrial process, determined victory in the Pacific. For Japan, The Type 92's failures represented the broader challenges of fighting an industrial war with artisan weapons. The gun's weight, complexity, and unreliability were symptoms of a military that had entered the modern age without fully understanding its requirements. The meticulous craftsmanship that might have impressed in peacetime proved disastrously inadequate when facing American mass production. The emphasis on individual marksmanship and precision could not compete with the American philosophy of volume and suppression. The Pacific War demonstrated conclusively that, in modern warfare, the ability to deliver sustained, reliable firepower determined victory. American forces, armed with M1919 Brownings, could lay down walls of lead that no amount of courage could overcome. Japanese forces, armed with Type 92 seconds, found themselves consistently outgunned. Their precise but slow-firing weapons, unable to match the overwhelming volume of American automatic weapons, the mathematical precision of American firepower, 400 to 600 rounds per minute from belt-fed weapons, overwhelmed the Type 92's 450 rounds per minute from 30-round strips. The human cost was staggering. Japanese infantry attacks that might have succeeded against enemies with comparable weapons were slaughtered by American machine gun fire. The banzai charges that had worked in China against poorly equipped forces became suicide against American firepower. Thousands of Japanese soldiers died trying to cross kill zones dominated by M1919s, their lives thrown away against an industrial killing machine they could not match. In the end, the contrast between these weapons tells the larger story of the Pacific War itself. The M1919 represented American industrial might, practical engineering, and understanding of modern warfare's requirements. It was a triumph of the adequate over the perfect, the practical over the theoretical, the industrial over the artisan. The Type 92 represented the limitations of a nation trying to fight an industrial war with weapons designed for a different era, built by methods suited for a different scale and employed with tactics from a different century. When American machine guns opened fire on charging Japanese infantry, the outcome was predetermined by design decisions made years before in factories thousands of miles away. The M1919 Browning had won the production battle long before it dominated the battlefield, establishing itself as one of history's most successful military weapons. While the Type 92 became a symbol of Japan's inability to match American industrial warfare, the Pacific War was ultimately decided not by courage, both sides had that in abundance, but by the ability to mass-reduce reliable weapons that could deliver overwhelming firepower. In that contest, the M1919's 390,000 units against the Type 92's 45,000 told the entire story.